Hello everyone, I'm Jae-Kwang Liu and I'd like to present our work titled The Rule of Masking for Efficient Supervised Knowledge Distillation of Vision Transformers. This paper was selected for ECCV2024 and I had the pleasure of working with Sung-Woo Son, Namun Lee and Jae-Ho Lee at POSTEC. Knowledge distillation is a technique used to compress the performance of a large model into a smaller one. A simpler model is trained to replicate the behavior of more complex model. However, knowledge distillation can be quite costly as the computation required for the teacher's forward pass often exceeds the combined cost of the students' forward and backward passes. So our question is, can we reduce the computational cost of knowledge distillation without degrading the student model's accuracy? We proposed MaskedKD, a method that reduces computational cost of supervised knowledge distillation for VITs without sacrificing student model accuracy. MaskedKD selectively masks the teacher's model's input based on attention scores from the student. The masking strategy works as follows. From the student's last layer, we measure the attention of class to patch tokens, averaging the scores across multiple heads. Then we retain only the patches with the highest scores. As a result, MaskedKD significantly can reduce the latency and computational cost of the teacher's forward pass. We observed that MaskedKD performs well across various teacher and student model combinations. For some cases, using only half of the teacher's inference cost, the student model not only maintained performance, but often surpassed it. This efficiency was consistent across different cases. Additionally, we found that MaskedKD consistently maintained performance across different feature distillation methods. We also observed that it performs well with models of different architectures and training methods, such as CLIP and large-scale models. We test MaskedKD in a different domain, especially in audio. When applied to the AST model, it achieved a 17 reduction in patch usage without performance loss. But there is a slight performance drop when using only 50% of patches. Next, we examined whether MaskedKD performs well in a recent approach where only the final layer is updated instead of full fine-tuning. We conducted experiments using higher resolution images. MaskedKD effectively distilled knowledge from teacher models trained at different resolutions, using interpolated attention scores. Finally, MaskedKD is applicable to tasks beyond classification, such as detection and segmentation tasks. To find the best masking method, we experimented with various masking criteria as follows. Among these, MaskedKD, in other words, student-guided masking consistently outperformed the traditional logic distillation. The follow-up question is, what makes the student-guided masking work well? Our answer is that it acts as an implicit curriculum for distillation. Student-guided masking makes the teacher's supervision easier for the student to mimic in the early stage of training. Interestingly, as shown in the training curves, the teacher's accuracy with student-guided masking is even lower than random masking. We found that randomly initialized VIT models often masks similar patches at once, sometimes removing all foreground patches, unlike random masking. Early student-guided masking makes it harder for the teacher to supervise central foreground objects. Another question concerns where we should apply masking. We compared MaskedKD with Tumi, a method that merges tokens at intermediate layers. Masking token at the input level is more effective for preserving supervision quality. Lastly, we investigate whether it's better to mask the teacher or the student. Even with a lower masking ratio, masking the student degrades the final accuracy, while masking the teachers does not. Thank you for watching video, and please feel free to contact us.